One thing that our CPU can't do is deal with fractional numbers. So for example, if we wanted to generate the sine or the cosine functions, which range between the values of -1 and +1, these all are fractional numbers, and we have no way of representing them. So we have to be able to represent fractional numbers in our CPU. So we have two ways of solving this problem. Within this course, we're going to look at the first solution, which is using fixed point numbers. Now in the next course, Design a CPU 4, we're going to look at solving this problem using something called floating point numbers. So if you like, the fixed point numbers is a stepping stone to the full floating point solution, which we will see in the next course. So the fixed point number system we're going to look at here is a bit of a cameo. That is, it's not going to be a full version. We only need to be able to get access to a couple of decimal places, and we just want to generate some trigonometric functions and a few other interesting mathematical functions. So we don't need to go through the full process of generating a full fixed point number system within our CPU. So let's have a look, and we'll take an example here. So I've picked out a number pretty much at random. So in our fixed point number system, we're going to have 16 bits to represent the number. The most significant 8 bits are going to represent the integer value, and the least significant 8 bits are going to represent the fractional value. So this is called 8.8 because we split the 16 bits equally. Now let's look at the actual integer value. So the integer value is this number here, and I've generated it down here again, and we work out the decimal from this binary the same way we do normally. The first bit here is going to be the value of 1, next bit is 2, 4, 8, 16, 32, 64, then 128. So this number here is going to be 1 plus 2 plus 8 plus 16 plus 64, which is 91 decimal. So that's 91 to the power of 10. So there's no change here. That's exactly as we have seen it previously. Now the change is in the integer part. So in the integer part, we're going to have 8 bits. Now the first bit is going to represent 1 upon 2. Then we're going to get 1 upon 4, 1 upon 8, 1 upon 16, 1 upon 32, 1 upon 64, 1 upon 128, and 1 upon 256. So this number here that we generate is going to be 1 upon 2 plus 1 upon 4 plus 1 upon 32 plus 1 upon 128. When we add these together, we get this number here. So then what we can do is we can join the two numbers together. So we're going to have 91.6445325. So this is a nice, neat little way that we can use to represent fractional values. So let's look at it in just a little bit more detail. If we were to have the fractional values here, so these are the 8 least significant bits, if they were all zeros, then this would represent 0.256, which is just the number 0. Now the next number up is going to be the value of 1. So that would be 1 upon 256, which is this number here. Now this number is an important number because it gives us the resolution of our fractional parts. So if you like, this number here represents a little bin, and that bin will contain all of the numbers between 0 and 0.003900625. So that's the first bin. Now the next bin up is going to be the 10, and that would be 2 upon 256. So if you like, it's 2 times this number. So we will have another bin which is the same width, okay, just up the number scale. So all of the numbers that sit within this range, we just stick it into this bin. Now we can continue doing this all the way up to the second last one, which would be 254 upon 256, which is this one, and then our 255 upon 256, which is this one here. Now it doesn't go up to 256.1256 because it starts from the value of 0. So 0 up to 255 is actually 256 values. So if you like, we could take this number here, and let's say we had a number, it was 0.9999999. Then we could pick that number and we can say, well, that number is actually between 1 and this number here. So we could pop it into this particular bin. And that's all we're really doing. We're just picking our numbers out. We're seeing which range they are within, and then we stick it into a particular bin. Now, there is a problem in that if we have numbers that are halfway between one bin and another bin, we have to decide which bin to put them in. And then we would have to work out some kind of rounding mechanism. Now, that's not something we really have to bother with here, because all we're really going to do is generate the fixed point numbers. But whenever we do a conversion to decimal, we will actually be converting them within a little bit of Python script. And that Python code will actually take the number and it will generate the full floating point version. So the actual rounding is going to be done within the floating points within the Python code. So it will be transparent to us. We won't actually see it. So it means that we don't really need to bother here with any rounding. And it makes things a bit simpler for us. Now, if we had to deal with rounding, then we could round down to the previous bin, we could round up to the next bin, or we could use something called nearest even rounding. So we would round to the next nearest even number. And the idea behind that is that statistically speaking, we will have half the numbers will be even, half the numbers will be odd. So we will put them into the upper bin and lower bin half the number of times, so there won't be any kind of systemic error. But that's more detail than we need. And if you're interested, you can always go online and check through and get more detail on the fixed point numbers and the mathematics and the rounding. But as it stands now, this is all we really need to understand. Now, there's one other thing that we're going to look at, and that is the fact that we are using 2's complement. So we're not going to represent numbers from our 0 up to approximately 256. We're going to have half the numbers are going to be negative and half the numbers are going to be positive. So it means that this number here, for example, will give us the largest positive number, which will be 127.9960935. And this number here will give us the largest, if you like, negative number, which will be -128. So this is our actual range of numbers. Now you might be looking at this and saying, well, that's not a very wide range and it's somewhat limited. So it is somewhat limited, and that's why I said this is a bit of a cameo version of our fixed point numbers. Now we could extend on this if, for example, we decided to use 32 bits instead of 16 bits. We could have 16 bits for the integer part and then 16 bits for the fractional part, and we could have a much wider range of numbers. Or equivalently, we could have, say, for example, 31 bits for the fractional part and only 1 bit for the integer part, and therefore we would have a smaller range of integer numbers but a much more accurate number in terms of decimal places. So there's lots of ways we could play this fixed point number system, and we could mix and match and generate different schemes depending on what it is we want to do. But that's more complication than we need. We just need to understand the 8x8 and we need to be able to implement it within our system. And this will give us approximately a couple of decimal places of accuracy. And that's all we really need to generate our basic mathematical functions. So let's go ahead and we will see how we're going to generate this within our CPU. So let's start off by looking at fixed point addition. we want to add the numbers 10.75 and 2.25. Whenever we add both of these together, we should get the number 13. Now the fixed point representation of these numbers are these two numbers here. So you can see the 10.75, the 10 is generated by the 2 plus the 8, which gives us the 10. And the decimal part here is going to be the 0.75. So 0.75 is 0.5, which is 1 upon 2, plus 0.25, which is 1 upon 4. So this number here is the 1 upon 2, and this number is the 1 upon 4. So we add both of those together, we get the 0.75. And again, we do the same down here. We change this number here into the fixed point version. Now, the great thing here about the fixed point version is that once we have the numbers within the fixed point representation, we can just work through the normal addition. So this means that there won't be any change to our circuitry. So whenever we add these together, you'll see we get to this point here and we say 1 plus 1 is the 0, carry the 1. 1 plus 1 is the 0, carry the 1. So you get a 1 at this point here. And then you get 1 plus 1 is the 0, carry 1. And you've got the 1 here. So whenever we work this out, we've got 0 here for the decimal or the fractional part, but we have 13 here for the integer part. So this works. We can just work through a normal addition algorithm. So the main point is that we don't have to change any of the circuitry to get this to work, but we're going to have to change the assembler, and we're going to have some extra section added into it, because we have to be able to generate these fixed point numbers from the decimal numbers. So let's look at that now. So let's start off by actually looking at the assembly language that we need to use in order to add the two numbers together. We're going to have a number 10.75 and a number 2.25. But as it stands at the moment, the assembler doesn't know anything about fixed point numbers. So if we were to put the number 10.75 in at the moment, it would be meaningless to the assembler. So what we're going to do is we're going to tell it we've got these special numbers, and you'll know that we have a special number because we're going to put the F in front of it. So anytime we want to represent a fixed point number, we're going to put an F in front of it. So F in effect stands for fixed point. So the assembler is going to come down here, it's going to go to the DC directive, it's going to find the label for it, which is X. So the X is going to be this number here. So as soon as it sees the F here, it says, oh, this is a fixed point number. And it's going to have to take this number and it's going to have to change it into the fixed point binary representation of this number. So it means that the assembler is going to have a little section which converts this number to the 16-bit binary version or the 4-bit hex version. So let's say, for instance, what the assembler has, we've built that little section of code into the assembler. So it means that we can have an X value and a Y value. It's going to come up here and we're going to load that X value into register R0. The Y value goes into register R1. So remember, the numbers that we're going to put in are going to be the fixed point versions of these two decimal numbers. And we've seen that we can just add them together like normal binary numbers, and it will give us a result. So whenever it comes out and it gives us a result, the result again will be in fixed point number. So in order to get the actual number, we ourselves will just take that number out and we will convert it to the decimal number, and that will be us will have our answer. So let's have a quick look at the actual assembler, and I will show you the section that has been added in order to do this conversion. So this is the full assembler here. Now remember, this isn't my original assembler which I wrote for the Design a CPU 2 course. This is the new assembler written by Timothy Morgan, and it's a much sleeker version than my older one. So once again, thank you very much to Timothy for putting the effort into generating this for us. So if we were to head down to round about line 600, so 600 and here it is here, 653, you can see here we have the conversion. Convert a decimal string to an 8.8 hex floating point number. So I have added the program into the RAM. Let's run it now. Now if this works out, we should get the answer 13, and answer 13 will be in register R1. So 13 in hex is going to be the value of D. So let's run this and see if we get this value. And there you see the answer here is 0D00. So the reason why we've got the 00 here is because there are no fractional parts. Okay, so those 8 bits are empty, and the other part here goes up to the number 128 approximately. So you can see the value here is D. Okay, so D is 13. So it does work, and it's generated the addition of those two fractional numbers. Now, I'm not going to go through the example of using subtraction, because if we were to go through and do subtraction, you would find out that subtraction works the very same way. So for addition and subtraction, it's relatively straightforward. We don't have to have any changes to our circuitry. We just have to update the assembler so that it recognises the idea of fixed point numbers. So that's quite cool, it's quite neat, and it gives us a nice, relatively simple and easy introduction to representing fractional numbers. So let's move on, and we will look at division and multiplication.